All right, hi Rivers class. Moving on with chapter 1, wrapping up after what I didn't get to finish today in class. We were talking about lanes balance, and we were talking about basin controls and how we have driving variables of water discharge and sediment flow that affect what goes on in the channel. And let me back up a slide, maybe not. There we go. All right, so some rivers are in equilibrium where the form is fluctuating around a equilibrium condition, but then we also have rivers that are not in equilibrium, and some rivers that are inherently not in equilibrium you could consider braided rivers perhaps to not be in equilibrium if they are constantly avulsing and aggrading. This is the Waiho River again, draining Franz Josef Glacier. The bridge we looked at in the slides today in class crosses the river here. It exits the Southern Alps and spreads out, and this was a big new deposition here. So other channels that perhaps are not in equilibrium because they don't have the continuous flow to form an equilibrium would be dryland channels or bedrock channels too. Only large floods are really influencing their channel form. It's not a continuous flow regime. Also, we have other factors like climate change, sea level rise, and human activities that can affect a channel's response. So if equilibrium is truly only possible if the sediment flow and the water flow aren't changing with time over long periods of time. So the river adjusts to the sediment water that has been provided to it over a long period of time. But if climate is changing and that the amount of water provided is continually getting bigger or getting smaller, then the river is going to have to adjust to that, and it's not necessarily going to be in equilibrium. Quote from your textbook author: it's important to realize that these regime dimensions represent an average and are not applicable to all channel types or flow regimes. So that's always good to keep in mind. But this concept of equilibrium kind of permeates the river literature, and so it's kind of good to understand what it is and also what the limitations are of it. So thinking about how processes influence form, but yet also form influence processes, we have our driving variable of the discharge of the river, which of course is a driving variable in determining the velocity distribution of the channel. But the velocity distribution of the channel determines the shear stress. The shear stress determines the ability of the sediment to transport, the ability of the river to transport sediment, which determines bedload transport, which affects channel form, which affects the geometry of the channel, which affects the velocity distribution. Also, what bedload is being transported affects the character of the bed material, which also affects the bed roughness, which affects the velocity distribution. We also know that the discharge of a river is not steady. It's unsteady. It changes with time. We also know that channel form is not uniform, and velocity distributions are not uniform. And so we can see there is complexity and variability in our system. Velocity distribution is also unsteady and non-uniform. Shear stress can be unsteady and non-uniform, and bedload transport can be unsteady and non-uniform, as well as our character of our bed material. So we have all of this complexity and feedbacks also in our river system. All right, I'm going to jump ahead to after lanes balance, which we talked about today. Okay, so one of our external basin controls can be the slope of a valley. So we're not talking the channel slope, because the channel can adjust its slope by incising or depositing, degrading or aggrading. It can also adjust its slope by meandering, right? So the more a river meanders, the flatter its slope. The valley slope is not, can't be changed that easily. Of course, over geologic time it's changed by rivers, but not over shorter periods of time. But it can give us an idea of potential energy expenditure along a given reach. So our boundary conditions are how confined our channel is by the valley. Is it confined, partially confined, or unconfined? What's our channel substrate, which can affect boundary roughness? Do we have bedrock, or alluvial channel? And then our riparian vegetation. So valley confinement, what we're talking about is the ability of the river to actually move around. So here's a great example on the Colorado River where it's quite confined. So this is high valley confinement. In this case, you have confinement on one side and unconfined on the other. Colorado River here in the Grand Valley is another good example of this, where you've got the south side of the river that's confined by the bluff, like for example towards Palisade, or not Palisade, Corn Lake. The south side of the river, it's confined by the bluff, the Orchard Mesa bluff, but the north side of the river is unconfined, so it's partially confined there. And then unconfined, the river has the ability to move around, and it can really create its own shape and form. And whoa, someone just tried to open my door. So another aspect of the boundary conditions in a channel is the riparian vegetation. And this is an example from British Columbia prior to logging operations and after logging operations. And they logged the riparian forest, and you can see the loss of that riparian forest caused the channel form to change considerably. Some of you are looking at, for your case study project, you're looking at rivers where riparian vegetation have actually encroached following dam, which can confine a channel into a tighter configuration. Okay, so one of the things we're going to be really thinking about is how do channels adjust with time? And also, how do they adjust in space? And this is a pretty standard look at both the spatial scale and the temporal scale over which river channel change occurs. And so basically, if we're talking small spatial scale, it usually means short time scale. So in sandbed streams, the actual bed configuration, we're talking small scale features that can change really quickly. Then we jump up to the actual channel geometry. How wide's the channel? How deep is the channel? We're at a little larger spatial scale and a little longer time scale. So this is our cross-sectional form. Then we move into bed configuration for gravel bed rivers. So a little larger spatial scale and a longer time scale. Meander wavelength, how far apart are meanders? Our plan form or pattern of our river, that's an even bigger spatial scale and then a longer time scale. Reach gradient can take, and so look at meander and reach gradient, we're getting up to the upper tens and then into hundreds of years. And then actually changing the valley profile, we're talking thousands of years, right? So that's longer time scale. So basically, the smaller spatial scale, the faster it changes as we get into larger time scale channel form components, then larger spatial scale channel components, then the longer the time scale it takes. All right, so that's it for that little bit.